Suppose we have these two vectors and we want to get the vector 3, 2 as a linear combination of them. We know we can get it by multiplying the first vector by 3 and the second by 2. The ones here result in the 3 and 2 that we get. In fact, for any two-dimensional vector, we can get the coefficients that we can use to give that vector. So we say that these two vectors fill the space of R2. R2 represents the two-dimensional plane of vectors made up of real numbers. We can have R3 having 3 components, x, y, z, R4 having 4, and so on. Let's have a graphical understanding for our example. As we saw, we can produce any vector in R2 using these two vectors. May it be 4, 2, 4, negative 2, negative 2, negative 3. But what about these two vectors? Do they fill the space of R2 as well? Again, filling the space just means that we can produce all the vectors in R2 using solely those two. Let's try to see if we can get to 11, 10 using the two vectors. This means we need these two components to add up to 11 and these two to 10. We can write these two linear equations as follows. To solve them, we'll multiply the second equation by 2 and get 2x plus 4y is 20. On subtracting the two equations, now we have negative 3y equals negative 9, which gives y is 3. We can substitute this y in equation 1 and get 2x equals 8, which means x is 4. So what this means is that we need to multiply the first vector by 4 and the second vector by 3, and then add them to get 11, 10. Let's verify this graphically. So here's our vector 2, 1 and 1, 2. We scale them up by 4 and 3 respectively and do a vector addition. The resulting vector is indeed 11, 10. So let me ask you this. Does every pair of 2D vectors fill the space of R2? To answer that, let's have a look at these two vectors, 4, 2 and 2, 1. No matter what linear combination I take from these two, it just stretches or shrinks either of the vector. The combination just stays on a single line. So what if I had negative 4 and 3? How do I get to it? Well, I can't, since it doesn't lie on the line. Therefore, these two vectors cannot fill the space of R2. They only produce vectors that lie on this line. So why do some pairs of 2D vectors fill the space of R2, but others don't? As an exercise, try to figure this out and we'll look at the answer in the next video.